We're going to start by looking at lines. And it's not going to take us a super long time.
We don't have a box.
Oh, no, it's just because I have a unnumbered graph as opposed to your numbered ones. It's the same thing. It's still 10. Mine's still 10 by 10.
No, we don't have that.
Oh, the glue box. The glue box. Yeah, I got it.
The wrong box.
That box. I thought you meant like the box around. I was like, oh, yeah, no, that's okay. You're fine. So we have two of our most common forms we'll see up here. This one we've seen, that's our slope-intercept. This guy's slope-intercept. What is our slope on this one? M. So this guy is our slope. So what is the B then? Our y-intercept. So we have two equations down here at the bottom. The top one, so this y equals minus 3x plus 2. This is our one in our slope-intercept form. So what is my y-intercept for this line? Positive 2. This guy's my y-intercept. So when I'm trying to plot this up and graph it, I'm going to put it on my y-axis at 2. Yours are numbered, mine are not, but that's okay. Same vibe. And what's our slope? Negative 3. How do I move with the slope of negative 3? We're going to go down 1, 2, 3, right 1. Down 3, right 1. And then I can do it again. Down 1, 2, 3, right 1. I can do it again. Down 1, 2, 3, right 1. The more points you put, the easier it is to make a straight line. So I can get this far on my graph with going to the right. I could also, instead of going up and to the right, or in this case it was down and to the right, I could go up and to the left. As long as I switch both arrows, it's still going to give me the correct slope. So I could go up 1, 2, 3, and left 1. That is another way I can go. Up 1, 2, 3, and left 1. It gives me that same line. So I'm going to connect these up. I'm going to use a ruler or a straight edge or the edge of an ID or the edge of a calculator or the edge of a phone. I don't really care, but when we have a line, we're going to use a ruler to get a straight line. But like the edge of your phone, the edge of your paper, the edge of your notebook, the edge of your ID, the edge of just about anything, post-it note, anything. There are rulers out and about. If you ever want one, I also have. I think else just got knocked off and put over here.
Thank you.
So our y equals mx plus b, that one is very, very familiar. We've seen that one before. The bottom one we have seen before, but it's not as common. Does anyone remember this one? Point slope. We have inside here, we have our slope. It is the same slope, and in fact, it uses the same letter. It is still our m. The other pieces we have in here, this x1 and y1, those are a point that is somewhere on our line. So if we look at this bottom equation down here, looking at this y minus 3 equals 2x minus 2. We're going to find all those pieces. What is the slope on this equation down here? I know it's very, very small. 2. This guy has a slope of 2. That's our slope. So if we think about our y minus y1, x minus x1. What is the value of x1? What is our x value of the point inside here? 2. X minus x1, so it's x minus 2. What is the y value of the point that's built in here? 3. So what's going to happen is we're going to start at this point when we're graphing it. So I'm going to start at the point 2, 3. So that point 2, 3, 2, 3 is right here. We're used to starting at our y-intercept and moving with our slope. But I can start at any point I know is on my line and still move with my slope. So we already talked about this is the point that was kind of been built here, and we know our slope is 2. How do I move with my slope of 2? Up to right 1. So I'm going to start from this blue point. I'm going to go up to right 1. Up to right 1. Up to right 1. And I'm just using these on the same graph because I don't feel like getting a second one out. If you want to do these on separate graphs, totally valid. We're not looking for the intersection. We're not starting it on systems. We're going to be looking at graphing today. Just kind of remembering how to do these. So our second line here is going to look kind of like this. These two. So when we're looking at this form up here, I just kind of copied it and gray right here. Just kind of match them up. The x's and the y's, those are going to stay there. So it's our x and y like normally we have here. It's this x1. This x1 tells me the x value of my point, and the y1 tells me the y value of my point. So we're just kind of matching them up. It's very similar to like the AH and K kind of guys, how H always had that opposite sign.
How did you know to go up 1?
The up to right 1, that would be because our slope here was 2. So it's matching up these same pieces. So this m is this m. The x1 is this guy, gives me that 2. My y1 gives me that 1, which gives me that 3. Good questions, good questions. So if we get linear equations in any other form, we can always solve them and be a slope-intercept form. And you can do that with the point-slope form too. You could distribute out the 2. I could then add 3 to both sides and make it be slope-intercept form. It's totally fine. It would work. We can do that. You can just adjust the form and do everything in slope-intercept form. We can deal with fractions. Okay? So questions on the lines. We're not going to do tons with lines because we've worked with lines a gabillion times. What we are going to focus on more is some of the other functions we did in Algebra 2. We're going to remember some parent functions. And then we're going to start talking about some transformations and those kind of things. So I'm going to put up a page that's going to have 3 graphs. These are the 3 we're going to talk about today. We're going to talk about quadratics, we're going to talk about cubics, and we're going to talk about square roots. With our graphs, especially when we have these functions, especially with ones with powers, we want a good view of what's happening in the center of our graph. And then things are kind of wild as we get a little farther away. So especially for parent functions, we're going to start in the middle. So a lot of times when we're looking at these, we're going to make a table. I'm going to kind of work down here. And then I did not give myself very much space to room, so I'm actually going to cover up a little bit of my graph so that I can make a table. A lot of times with these, it's going to be helpful to make a table. You don't have to, and especially when we're thinking about parent functions, if we don't need to make a table, that's totally okay. But for these first ones, I kind of want to make a table. We want to know what's happening in the middle of the graph, so I'm going to put in the middle of my table 0, because that is where the middle of my graph is. Right there. I want to know a couple of things bigger, a couple of things smaller. So for the most part, when we're working with our parent functions, we're going to be looking at 0, 1, and 2, -1, and -2. And for right now, we're going to deal with quadratics, not doing tons of transformations, just looking at A and K today. But we're going to start with just looking at our parent functions, which is when neither of those things are happening, so we're just going to look at x squared. So let's see what happens at y equals x squared. What is 0 squared? 0. What is 1 squared? What is 2 squared? 4. What is negative 1 squared? 1. I'm going to zoom this in because I know I'm writing very, very small and at the very, very bottom. What is negative 2 squared? 4. So with our parent functions, we don't have anything else kind of going on. We can just kind of think through those values. I know whatever my x is, if I square it, that's my y. So if we were to plot up these points, we'd have our negative 2, positive 4. 1, 2, 3, 4. Get a point right here. I'd have my negative 1, positive 1. We'd have a point at 0, 0. That's going to be my vertex. Point at negative 1, point at 1, 1, and a point at 2, 4. We could go out farther. I could know what happens at 3. What would 3 squared be? 9. So if I went out to x is 3, I could get a point up at 9. Same thing with negative 3. I could have negative 9. We don't have to go all the way out that far. If it helps you, draw it. If it doesn't help you, don't draw it. But for our x squared, this is kind of what it looks like. These ones we don't use rulers on. We can't. Because it's not a line. So it's going to be kind of U-shaped. Those are our quadratics. And when we start looking at some of our transformations, we will use that parent function or that parent table to kind of shift things around to get them to be where they're supposed to be. We did a lot with A, H, and K in Algebra 2. So if we think about cubics, they're very, very similar. We're going to think about our parent function for a cube, for x cubed.
Yep. I'll wait.
Totally fine. We're just going to look at our x cubed right now. And then our last one, we'll look at our x squared. Okay, so with x cubed, again, I want to get a good view of the middle. I want to know what's happening in the center of my graph. So when we're picking our x's to work with, we're going to pick pretty much the same ones. I want to know what's happening in the middle. So we pick our x's to find our y's. And so we like to start in the middle. So I'm going to start at 0. I want some numbers bigger, and I want some numbers smaller. So again, typically we just take 1 and 2 that are bigger, and -1 and -2 that are smaller. You don't have to use those ones. They're just kind of habit. It gives us a good view if we continually pick those ones. Makes patterns kind of easier to see. But you don't have to use those ones. So if we think about cubes, looking at our x's that we picked here, what is 0 cubed? 0. Again, this is our y equals x cubed. I'm just going to write it down here so I don't have to zoom up quite so far. What about 1 cubed? I was looking at 1 cubed. So that's just 1 times 1 times 1. It's going to be 1. What about 2 cubed?
8.
8. 2 times 2 times 2. What about -1 cubed? negative 1. Oh, sorry, that's 8. I wrote wrong. What about negative 2 cubed? Negative 8. So when we plot up these points, it's going to look a little bit different because we now have our negative 2, negative 8 way down here, negative 1, 0, 0, 1, 1, and 2, 8, which is that one. So we get something that's kind of an S shape, like a wonky S. And this is our parent function for cubes. So I could take that and I could apply all kinds of transformations to it. I could move things left, I could move things right, I could stretch, I could compress, anything like that. Our other one we're going to talk about today is square roots. I'll get just a second because I know I'm zipping. So if we think about the square roots, we could 100% pick the same x values to work with. However, when we're looking at our graphs here, we can't graph anything imaginary. Not on this kind of graph. We're not going to have graph imaginaries in here. So I don't need to pick x values that are negative because I don't need any imaginary numbers. I could do it, but we're not going to graph any imaginary numbers. We're only going to graph in the reals. So I don't need to take the negative 2 or the negative 1. I can still take my 0. I can do the square root of that. I can still take my 1. Do we want to do square root of 2? Not particularly pleasant. What would be another number that we could square root nicely? 4. And if we feel like having another one, we could do 9. Square roots are really the only ones where we typically pick different x values simply because I don't want to do square root of 2 as a decimal. Gross. Yeah. I don't want to. So to make our lives easier, we pick our x's that are perfect squares. Other than that, it's the same process. The square root of 0 is going to be 0. Square root of 1 is 1. Square root of 4 is 2. And the square root of 9 is 3. We're only looking at those positive square roots, like because typically when we were solving, we plus or minus. We only look at those positive square roots because we want this to be a function, which we'll talk about what those are a little bit later. And when we plot up our points here, we've got our 0, 0, our 1, 1, 4, 2, way over here, and then 9, 3. This one, when I connect it up, I'm not going to go left of the 0. I don't want to wind up with negative x values because then we get imaginary y's. That would be bad. I stop right there. It only has an arrow on one side. Because what these are square root and our square. Those are our inverses of each other. If I was to floop this guy on its side, I'd get exactly the square root. We just only take the top half because then it's a function. I'm going to zoom out to see the whole page here so you can see the whole thing.
It is on the whole thing.
Huh?
It's already on the whole page.
I know. Well, it's just, then it doesn't zoom it in. Because then I can, oh, see, I didn't lock it out. There we go. Now it's on the whole page and I can zoom in to write things and it doesn't zoom in for you guys. That's why sometimes when I have it zoomed all the way out and I have to write it big because I can't zoom in and my screen's very small. So we're going to take these graphs, these parent functions, and we're going to remember about transformations and what they do and what they're called and all that jazz. Okay? Questions on our parent functions. Why do I have a graph on this page? Here we go. Because we're going to talk about our transformations here. We've dealt with A before. A, which will do our stretch or compress. And A is going to stretch our graph if A is bigger than 1. If A is littler than 1, it's so little and cute. I want to squish it. So it's a compression. Because it's so little and cute. H will do a horizontal shift. We've worked with that one a bunch. I feel if I don't put it in there, we tend to get a little confused. And K is a vertical shift. What we're working with today, we're only going to see the A's and the K's because that's the way the book divides it up. But if I don't talk about H, people are like, wait, what happened to H? And this is in general when we're talking about our transformation forms. I'm going to put for quadratics up here. That's our y equals a x minus h squared plus k, like that kind of guy. H is always inside the parentheses or inside the radical or inside the cube, inside with the x. K is added on the end. A is out in front. Yes, sir.
Does the A stretch when it's bigger than 1 or what?
When the value of A, so think about like absolute value. If A is larger than 1, so it could be 2, and it would stretch, or it could be negative 2, and it would stretch. It would just reflect. If A is negative, it reflects across the x-axis. Forgot to mention that part. So A will do a vertical stretch. If you want like a shorthand for it, vertical stretch would be if the absolute value of A is greater than 1. So it could be positive 2, positive 3, positive 7. Could be negative 2, negative 3, negative 7. It's still going to be a stretch where it gets tall and skinny. It's stretching. If our A is little, if it is smaller than 1, so our absolute value of A, I'm going to do it in a different color so that it's tracking the thought. If it's compression, then our absolute value of A is less than 1. 1/2, 1/4, 1/3, 7/8, 1/16, negative 1/16. Anything like that. If it's littler than 1, that's when we're compressing. It's so little and cute, I want to squish it. Compression. And what that's going to do, compression looks like somebody sits on it, so it makes it look flatter. Stretch makes it tall and skinny. Compression makes it short and wide, flatter. Looks like somebody sat on it. Because it's so cute and little, I want to squish it. Squish. If A is negative, that's when we get our reflection over the x-axis. So A would need to be negative. H is just a shift left or right. K is going to be a shift up or down. So when we're looking at these transformations, a lot of times we're going to use that parent table to help us make our new graph without having to think the whole thing from scratch. So if we look at this y equals minus 2x squared, we have an A here. What is the value of our A? Negative 2. What do we expect to happen transformation-wise when our A is negative 2? It's going to reflect over the x-axis, so it's going to flip upside down. And stretch. So it's going to get taller. A lot of times the way we do this, or at least the way we did this in Algebra 2, which we're going to continue, we're going to take our parent, that one we thought on the last page where we had our x's, then we found our y's. We started at 0, we got some bigger, some smaller. So we have our 0, 1 and negative 1, 2 and negative 2, or negative 2, negative 1, 0, 1 and 2. And our parent function will always be the same. For quadratics, it's always going to give us a 4, 1, 0, 1, 4. 2 squared is 4, 1 squared is 1, 0 squared is 0, negative 1 squared is 1, negative 2 squared is 4. We do not need to graph the parent function with it. When we do our transformation form, this is when we had a lot of us, we'll do our x plus h, and then we always remember how much graphing makes us yak, ya plus k, that guy. We don't have any h's here, so our x's are going to be the exact same. We don't have a k here either, so all we got to do is take our y values and multiply it by the a. So our x values aren't going to change. They're going to be exactly the same as our parent, our negative 2, negative 1, 0, 1, and 2. Those guys aren't changing
Why not?
because we don't have any h's. There was no h inside the parentheses with the x. If we had an h, it would be inside like this guy. And I also don't have any k's because I don't have anybody plus on the end. So that's not changing anything here. What we're going to do is we're going to, we're going to take our y's times our a. So I'm going to take my 4 times negative 2.
Negative 8.
Negative 8. And we're going to then take our 1 times that negative 2. 1 times negative 2 is just negative 2. We're going to take our 0 times that negative 2. 0, because 0 times anything is 0.
Can we graph the parent function if we want to?
Yes, absolutely fine. If it helps you to graph the parent function, go for it. And then we're going to have our 1 times negative 2, giving us another negative 2. And our 4 times negative 2, giving us a negative 8. If it helps, absolutely fine to plot up your parent function. You can do that. I'll put it up here for those of you that like that. 2, 4. It's going to look like this. So this is your parent. You don't have to graph the parent, but it's here. When we are graphing our function, we're going to have our negative 2, negative 8, which is down here, negative 1, negative 2, 0, 0, 1, negative 2, and 2, negative 8. So this is our new quadratic. And we can look at this and we can see that this has in fact been reflected across the x-axis. This whole thing got flipped upside down. And it's taller. This one was up 1, this one went down 2. It's farther away. So these pieces have been stretched. A, H, and K have the same jobs no matter what kind of function we're looking at. And since we've worked with these kinds of graphs before is why they've kind of taken them all and jumbled them together into this one section. But that's what we're going to do is we're going to take our A and K, honestly, because that's all they give us in here, and we're going to apply them to the other functions we graphed at the beginning. questions on this one? So the next one we're going to look at is going to be a square root.
Yay.
So here we have that y equals this 2 times the square root of x plus 1. And we're going to try and graph this thing. And yes, we could just kind of blindly pick x's, hope for the best, and aim for some decimals. Good luck. Not going to be super easy. We're going to do this using our transformations. So we're going to start by getting our parent table for our square roots. I'm going to just kind of need butter into myself because I know it's going to take a second for us to get graphs where we want them to be. Yes.
I get another issue.
Absolutely. I always have extras. I always have tons. And if you ever just want plain graph paper, I have that too. Plain graph paper, sided. I think I have in here some printed out graphs as well. Also have some plain graphs. When I'm done with those, I'm going to cut them up and give them the bucket of strips. So we have lots of options. So since we see a square root in here, we're going to start by thinking about our parent function. That's our y equals the square root of x. That was our kind of starting place. I'm going to move that down a little. I don't like it being quite that tilted. That was the one we did pick different numbers for our x's because I don't want to have to square root negative numbers because I don't want to have to graph imaginary numbers because ew. So when we had our square root of x, that's when we picked our perfect squares. So we usually pick 0, 1, 4, and 9. Because we know the square roots of those without having to type it in the calculator and get a decimal. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and the square root of 3, or square root of 9 is 3. There we go. So when we look at this up here, thinking about our transformations, we think about our y equals a x minus h plus k. What pieces do we have here in our equation? We have a and we have k. What is our a? 2. That's the number multiplied out in front. A will always be multiplied out in front. What is our k? Positive 1. So our a is a positive 2. Our k is positive 1. So that means I expect this to be stretched because that a is 2. And when my k is 1, which way does k move us again? Up. Think of k as a kite or as a kangaroo. They just go up and down. When we get into ages, age is the hula. Go side to side. I will do that beautiful hula every time. When we're making our transformation form, we're going to take our parent function and we apply our transformations. Every time we're going to have our x plus our h. We don't have an h here. And we're going to remember how much graphing makes us yak, ya plus k. So our x's are going to be exactly the same because we don't have an h here. So we're going to have our 0, our 1, our 4, and our 9. And then we're going to take our y values from over here. I'm going to take my 0 times our a. So we're going to go times 2 and then plus 1. So we take our y's from our parent function times 2 and then plus 1. So 0 times 2, 0, plus 1 is 1. Then we're going to have our 1 times 2, which is 2, and then plus 1. So we're going to have 3. For our next y, we had 2. 2 times 2 gives me 4. And then plus 1. gives us 5. 3 times 2 gives me 6, plus 1 gives me 7. So we can plot those points up. We're going to have our 0, 1, our 1, 3, 4, 5, and 9, 7. So this is our transform function. And if we think about that one compared with our parent, which looked like this, we can see that it did get stretched vertically, and then, helps if I actually plot these right, 0, 1, here. I'm good at counting. I had it zoomed in too far. I plotted 2 of those points wrong. There we go. Ooh, too far. Yep, nope, that one and that one I plotted wrong. I'm good at things. 1, 3. There we go. The other points were fine. I just had it zoomed in too far, and mine isn't numbered. There we go. That way. So it got stretched and shifted up 1. Okay. So we can apply these transformations to all kinds of functions, all kinds of pieces that we've worked with before.
That's totally not suspicious.
We can work with our quadratics, we can work with our cubes, we can work with our square roots, all that kind of stuff. Let's do one more, because they like to throw these kind of ones at you a little bit.
Jeez Louise.
We'll do this one. This will be our last one for today. We're going to do x equals 1/4 y squared. Ew. Yes. It's like you can do that. The only downside with that is since we have an x equals here, we're not going to necessarily have a function, so we would need to make sure we got both plus or minus on the square root. Since we're doing the square root, it's not a part of the function. The other option here is to think of this as ew, gross, and say, what happens if I just look at the y equals 1/4 x squared as an equation, and then at the very end I go, okay, swapsies. So I'm going to make my table for y equals 1/4 x squared, and then I'm going to swap the x and the y columns to get it into the gross. So if we think about this table, the y equals 1/4 x squared, that's looking at our quadratic parent. I'm going to draw 3 tables on this one, where we'd have our -2, -1, 0, 1, and 2. And we'd be looking at our 4, 1, 0, 1, 4. So that's our quadratic parent. If we want to get 1/4 x squared, that's when we would take our x values exactly as they are, and we're going to multiply our y times 1/4. Going to be decimally, and that's okay. So our x's are staying exactly the same, -2, -1, 0, 1, and 2. If I want my 1/4 times y, so 1/4 times 4 is going to give me 1. 1/4 times 1 is 1/4, 0, and then we'll have another 1/4, and then we'll have a 4. Not plotting that one either, because I want to actually plot up the the top one where we had our x equals. So from here to here, I just switched my x and my y because this is way easier to make a table for. So now to get the graph of this, I'm going to switch my x and y again. So I'm going to take these guys and flip-flop their columns. I sure did. Boop. I'm just totally making sure we're paying attention. Absolutely. Totally. So to get my graph of this, I'm going to say, all right, I replaced my y with the x. So I'm going to put all the things that were in the x column, that -2, -1, 0, 1, and 2. And my x's are going to be what was in the y, because I had swapped it here. 1, 1/4, 0, 1/4, and 1. Ugh. Gross. When we plot this up, it's going to look weird. Because we have our 1, -2, 1/4, -1, zoom right there, 0, 0, 1/4, +1, and 1, +2. We have a sideways parabola. It's not a function, but we can do it. We're not going to do it often, but they sometimes throw those at you. So if we have a function that we know what it is, if I was to flip-flop my letters, flip-flop your letters, do it the easy way, and then switch it back. Kind of like doing a U substitution, but with graphing. Okay? I'm going to leave this here for just a second. So most of the a lot of the start of homework 2 is just sketching graphs. They don't have to be perfect. We're getting the vibe. I will put the pages up. Boop.
Can I get
Mm-hmm. Yep.
Faye, could you bring me the